So wait for a few minutes and then we'll start. So I'll wait for a few minutes and then we'll start. Okay. Okay. Am I audible? Hello. Hello. Am I audible? Okay, fine. So, I don't know why people are not coming. This is supposed to be, uh, I think, for tutorial sessions, one of the most important uh, tutorial. But if you have any questions regarding the assignments or the previous classes, please unmute and ask. Okay. Uh, yeah. Or do you find the assignments are solvable or not? Okay, you can just unmute and ask actually. That is fine. Yeah. So then I'm not going to solve the assignments, and I think this week's assignment is based on SSH model and maybe Kita chain, right? Because I'm not able to access the assignments, and they also are not giving access, and because they're saying that uh, I need to create my own assignment, which is fine, but I need to see also the assignments which are given. So Sajid, the questions are related to the only SSH model and Kita chain. Anyway, uh, so we'll start. Today I'll describe SSH model. Okay. This is one of the very intuitive and simple model to understand topological insulator and how it differs from the conventional insulator. Okay. This is a fairly big topic, meaning there are a lot of details into it, but I'll try to cover it up as much as possible within these 2 hours, let's say. And some part of it is already quite detailed uh, information, or the lecture is done in the, I think, week 2, lecture 1. But there are some aspects which I feel we can understand this from a complementary point of view with more details, let's say, right? So this was a model proposed by these three gentlemen, Wu Pei Su, and then John Robert Schiffer, and then Alan J. Heger, okay, in 1979. So they used this model to explain the increase in conductivity in the polyacetylene polymer, which looks like this, right? So we have a carbon-carbon bond, and then there is carbons are associated with, there is a bond with the hydrogen as well. Now there are two types of bond, as you can already see. So this is a double bond and then single bond. Uh, so this is a 1D kind of polyacetylene or polymer chain that was introduced to explain the polyacetylene polymer. Okay. I mean the increase in conductivity in the polyacetylene polymer. Now this has been adapted to understand the phase, topological phase, and how it differs from the conventional trivial phases. Okay, so we'll interchangeably use SSH model or Schiffer-Heger model uh, as per their last name of these three scientists. Uh, I'll try to cover up these three things. So these five ideas actually, as much as possible. Okay. So we'll see what is topological insulator, what is the role of band twisting, and what is it, what is the band twisting. And then there is a topological index called winding number. Uh, we'll also talk about bulk edge correspondence, and then symmetry protected topological phases. So these are sort of ideas that Let's see how it goes. I mean, how much I can cover. So if you have any questions, please ask regarding the previous lecture or the previous assignment or even the current assignment, assignment 2, let's say. Else, let's start. Okay. And please feel free to stop me and then ask because this is really crucial to understand the big picture of novel phases of matter actually uh, yeah, I mean, in fact, this is one of the very simplest example that you can work out by hand almost and then get a feel what is going on. Okay. Okay, so with this, if we have no question, then we'll start with simple insulator and then slowly move and build the story towards the topological insulator. Okay. So imagine you have we take a tight binding lattice where these are my atoms, A type and B type. These are one unit cell, let's say. So this is one unit cell. And this is an infinite chain. So again, we'll have unit cell uh, of similar type, A type of atom and then B type of atom. And it goes on. Okay, it goes on both sides. And these are unit cell. Now, imagine or assume that the hopping from A to B of the electrons is measured or represented by T. So everybody is familiar with the tight binding model, right? Can anyone, I mean, if you are not familiar, then it will be difficult. So then maybe I will introduce uh, very briefly. Okay, yeah, okay, fine. So let me think about it. How much can I do? Yeah, so so have you completed the condensed matter one course? Actually, this is a prerequisite condensed matter one. Okay, so this will be difficult because if you have not completed condensed matter one, it might be difficult. But so tight binding, I mean, approach is basically get to so the way we derive the energy spectrum of any let's say material. Okay. So what this necessarily mean is that I have some periodic solids, okay? In the periodic solids, so let's say I have a solid state system, 3D, 2D, 1D doesn't matter. And then the these periodic solids are essentially made of each unit cell, right? Periodic unit cell. And within the unit cell, there will be some atoms. So the simplest picture to, let's say, work in this 1D picture that we have already done, but then similar idea can be easily extended to 3D or 2D even. So what really happens is that these atoms will have some orbitals, right? So as you know, or atomic orbitals. So whenever we have atoms, you take any atom, I mean carbon, hydrogen, etc. So there will be some orbital starting from s orbital, which is spherically symmetric, and then p orbitals, and then d orbitals. D orbitals will have some four lobe at least. So these uh, so in the solid state system, suppose within an atom, sorry, within a unit cell, you have two atoms, okay, A and B, and for simplicity, let's assume so they are made of uh, some P-like atom, and this is a B atom. So let's assume that there is S-like atom, okay, S wave or S and P. So these are atomic orbitals, okay, atomic orbitals. Now, what can happen is that as you have read in quantum mechanics that so these atomic orbitals have their some finite spread in the real space. And then there is, of course, the atomic potential, right? The, I mean, because of nucleus and so on. Now, the electrons in the system or electrons associated with the atoms, let's say this is the atom, one type of atom having pz orbitals, okay, and this is s orbital for the b atoms. Now, electrons from the pz orbital can hop to the s type of orbital in the adjacent atom, okay, and because of this, uh, so then this will develop some energy spectrum for the, I mean, for the electrons, right? So electrons have a finite probability from going from, let's say, pz orbital to s orbital, and then vice versa, s orbital to pz orbital. And if there are other atoms within the unit cell, that then all the hoppings are essentially, I mean, finite. And there is associated energy with which these electrons can hop from one orbital to another orbital, and we usually denote it by T, or sometimes other notation as well. Okay, and using this atomic orbital, I mean hopping from that one atom to another atom, we construct the Hamiltonian. Okay, Hamiltonian for this unit cell. And because the periodic solid is made up of, I mean, made up of this type of unit cell getting repeated, right? So we need to only solve for this unit cell and construct the Hamiltonian for the electrons, and consequently we will get, so you will get the Hamiltonian, and then will have some, I mean, wave function which will be consistent of atomic orbitals AO, right? Because you are essentially constructing the Hamiltonian from the atomic orbitals. So you will solve H psi equal to E psi. There are various ways of solving it. One is numerical ways of doing it is DFT, density functional theory. There are other ways also. But essentially, when we call tight binding model, we assume that the atomic orbit or the electrons with, let's say, this is A type of atom and this is B type of atom. This is PZ and then there is S. The electrons are tightly bound. Okay. So suppose I have a electrons for this atom, A atom. I have a electron here. So they are tightly bound to that atom only. Okay, so if we are talking about electrons from the A atom, so there will be a nucleus surrounding that. There will be, I mean, the atomic orbitals where the electrons will be there. So they are tightly bound to that atom, but then there is a finite probability. Okay, they are not free electrons. So what do we know about free electrons is that I have a plane wave like solution, right? It will be plane wave like solution. So I will be to the power I k dot r. They are not tightly bound. It can have, I mean, it's a periodic in momentum space, and they are non-localized, right? Non-localized. So they are free to move actually within the whole, uh, I mean, space. Okay, and they have a typically energy spectrum as h bar square k square by 2m, right? That's the energy expression, free energy or free particle. Now, in these cases, often in the solid state system, what really happens is that they are not really free electrons. I mean, not purely free electrons. So energy is not going to given by h bar square k square by 2m, rather some complicated function. Okay, we'll see one example as that of that. Okay, simple, but yeah, we'll see. Uh, so these so the electrons are tightly bound to the corresponding atoms, but they have a finite probability to hop to the adjacent atoms. Okay, it is not that I have a, let's say, periodic solids, I mean, extended up to big length, let's say, and then it so as you increase, let's say there is another atom of the next unit cell. So this is my one unit cell. Okay, and this is another next unit cell. So the hopping from this to this is uh, exponentially suppressed, let's say. Okay, so the hoppings are short range. Why? Because electrons are essentially tightly bound to the corresponding atom, but they have a finite probability to hop from, and this is kind of, you can think of as a quantum tunneling, right? Classically, if you think, then there is no tunneling probability, but then quantum mechanically there is always a finite tunneling probability from one potential to another potential barrier, right? But as you increase the distance from this their parent atom to the other atoms, the tunneling probability also decreases. So the hopping probability also basically decreases. Okay, so basically they are more or less tightly bound, yet they have a finite probability to hop to the nearest neighbor mostly. Okay, in some cases the next nearest neighbor at max. And that's how we solve there are many various methods. We solve we construct the Hamiltonian first, then solve the Hamiltonian to get the energy and then wave function. Okay. Uh, so with this, let's move to the main topic. Okay. Because tight binding model itself is a chapter in itself if you do condensed matter one course actually. Okay. Okay. So if you have any question, please ask. Uh, yeah. No, usually they are not. So hopping amplitude should not be different from A to B and from B to A. There are some special materials or some materials where they can be different. I mean direction dependent hopping, which we say. But they are usually, for our case, in this course at least, we are almost never going to consider that um, from A to B and B to A is not going to be different. What can be different, and in this lecture itself we will see that so this to this can be different. Okay, let me use different colors. So this to this can be different because you are going from one unit cell to another unit cell, and the one realistic example you can see is that let's say, so in the polyacetylene polymer itself, so let's consider, if you consider this to be your unit cell, then from this to this and this to this can be different, right? Or even if you, yeah, so this can be different, this one and this one. So if you are going to the another unit cell hopping, then it can be different. Otherwise, we'll, for all practical purposes, will not consider. Yeah, that will be there. Okay. Yeah. Okay, so we'll come to this actually, this particular different hopping. But for now, let's consider, I mean, so this is the one atomic chain we consider, where we have a arrangement of A type of atom and B type of atom, and they are, let's say, same orbital. Okay, if they are s orbital, then both the atoms have s orbital. Okay, and they are only allowed hopping is let's say if from A to B, and we usually give a minus sign to T, but this is purely conventional, not an issue if you work with plastic as well. Okay, and this to this is not allowed now. Okay, we'll consider the this case in the later stage. So, so these are atomic chains. Now what we are interested in is the energy and the wave function of it. Okay. So, what will be the energy? So, as I have said that you only need to talk about the unit cell. You don't need to take into account of all the unit cells because the units, every information is already there in the unit cell, and you just repeat the unit cell to get the whole lattice, right? So the Hamiltonian will be what? So this is in the A and B sublattice. So what we have is that from A to B there can be a hopping, right? With a hopping amplitude of minus t. So this is 0. A to A there is no hopping we are considering. So this is A and this is B. So from A to B there is a finite hopping amplitude of minus t, and similarly from B to A this is also the same, right? Minus t. So this is B to A, and the B to B is 0. So this is the simplest Hamiltonian. And if you solve this Hamiltonian, what will be the eigenstate? So eigenstate will be 1 by root 2, 1, 1, and then 1 by root 2, 1 minus 1, right? So if you once you solve this, so this will be the bonding orbital with energy, let's say minus T, and then this will be the anti-bonding orbital. So bonding anti-bonding essentially means so the bonding orbital, let's say we have A type of atom, B type of atom. Bonding orbital will be something like this. They will have a finite probability, I mean finite overlap, and then anti-bonding will be the opposite. Okay. Uh, so this is the same concept we know from chemistry. So this will be, let's say, anti-bonding orbit. They will peak at the atomic position and B. Yeah, so this is bonding and this is anti-bonding. Okay. So the bonding orbital will have energy minus T, and then anti-bonding will have energy of plus T. Okay. So if we write the Hamiltonian in the real space, so we have site. So this is the unit cell index. Okay. So this can go to from, let's say, we label it from 1 to, let me label it a different color. So let's say this is unit cell 1, this is unit cell 2, 3, 4, and then somewhere here 0, -1, and so on. It goes on. Okay. We are taking infinite chain. So unit cell index I summed over all unit cell, and then hopping amplitude of minus T and CIA dagger. So these are second quantization language, CIB plus CIB dagger CIA. I'll explain what these terms means. So what this necessarily means is that Ci is the creation operator, and then this is the CIB is the annihilation operator. Okay. So this term combinedly means that I have a hopping from, let's say, so I had a type of atom, B type of atom. So what I have done in this term, where this term explains that from B atom, one electron is annihilated, and then here one electron is created. So this is equivalent of saying that from B type of atom, one electron has been transferred or hopped from B type of atom to the A type of atom. Okay, so this is equivalent to this picture. Okay, and then there can be similar process. A type of atom, I mean electron from A atom can go to the B atom. So so essentially going uh, from A atom means that there is a annihilation of an electron, which is represented by CIA, and then there is a creation of an electron at the B side, again determined by, sorry, represented by CIB dagger. Okay, so this is a second quantization notation of writing tight binding Hamiltonian, and this we are in the real space. Okay, and how the energy looks like, we already know that energy dispersions, or sorry, energy, there are two eigenvalues. So we have a Hamiltonian of 2 by 2, right? So this is a 2 by 2 Hamiltonian. Once you diagonalize this Hamiltonian, you will get 2 energy, right? So we already know what are these energy. One is energy equal to minus T, one is energy equal to plus T. So if you plot the energy, let's say, and as a function of, let's say, position of the unit cell, right? So each unit cell have an energy of two value. There can be two value. So one is, let's say, plus T, and another one is minus T. So this is for, let's say, nth unit cell. Okay. And then there similarly there can be n plus 1th unit cell. So this is n plus 1th, and then n plus 2th, and so on. And but important point is all electrons, sorry, all the energy levels are equally distributed, meaning there will be one plus T energy state and another one is minus T energy state. And then there is a difference between 2T, difference of 2T between these energy eigenstate. And if you have, let's say, half filled case, and this will continue, okay, along this direction as well, along this direction as well, infinite system basically. So what we have is that, let's say, so if you have a half filled case, let's say, what do we mean by half filled is that so there are two energy state and the number of electrons in the system is such that it only fills the lower energy state, right? Once you have electrons, they always want to be in the lower energy state. So the electrons are here, let's say only, and they continue to in the lower energy state. So this is the case of half. Sorry. So this is the case of half filled. So how many case will be there? So the n, if we assume that the n is the number of total site, okay. So let me call it I, otherwise it will overlap. So this is I plus 1 and I plus 2, I plus 1th unit cell, I plus 2th unit cell. So let's say total number of cell is unit cell is n. So number of unit cell and n can go to infinity. Okay. Okay. So so that means that there is n number of electrons, right? N number of electrons. So n number of electrons are there. So this is a case of half filled. So why we are calling half filled? Because the system has 2n number of total states, right? 2n number of total states. So please remember that we are not considering spin into the picture. In fact, in the whole lecture, will not be considering spins. Okay, because if you consider the degeneracy due to spin, then there can be, I mean, 2n number of state for this lower energy itself, and then for the higher energy also there will be 2n because you can have up spin and then down spin. We are not considering spin here. Okay, so we are assuming that we are having spinless fermions, and then there is n unit cell and each unit cell have a two energy states. So these are the two energy states, and because there is n electrons in the system, so they will initially occupy all the low energy states, so that all the low energy states here are filled out of two n total states. So two n total states. So filling is given by number of occupied state by number of total available state. Okay, so we have n number of occupied state here, and then total number of state is 2n. So this is half. Okay, the filling factor is half. That's why we call it half fill. Okay. Now, if this is the case, then basically what happens is that so your real space picture looks like this, and then if you go to the K space by Fourier transform, so you do Fourier transform. So why we are doing this, it will be clear as we go along. Okay. So Fourier transform, if you do of the Hamiltonian, let's say, then so we are in the real space and then we are trying to go to the K space, let's say. Okay. So that's what the Fourier transform does. And again, we will have a similar Hamiltonian. So the creation and annihilation operator now will be in terms of K. Earlier it was having, let's say, the I index, right? The unit cell index in the real space, but now it will have K index. So KB, and then it's Hermitian conjugate, right? If you see this picture, so this energy landscape picture in the K space, you'll see something very similar. So again, we'll have uh, so now energy will be a function of K, and so so again the energy. So there will be two eigenenergy. One is plus P, and one is minus t. Now, note that here we are denoting the energy as a continuous, right? Because essentially, when you can do Fourier transform is that when you have a periodic system from real space to k space you can go. So we have a n number of states, let's say, and we are in the first Boolean zone, let's say. So this is k momentum, and we have a minus pi by a, let's say, and pi by a. So a is the unit cell dimension of unit cell, which we are going to take 1. Okay, so this is essentially from minus pi to pi. And we have a continuous energy spectrum at plus t and at minus t. So again, if you talk about half field, then all the electrons are filled here. Okay, again the filling is half because there can be same number of electrons here also, which is not filled. And yeah, so so the reason we are sort of studying this is that at the half filling, okay, so at the half filling, when you have you have this kind of chain, sorry, yeah, so when you have this kind of chain, okay, at the half filling the system behaves as an insulator. Why? Because all the lower states are filled, so essentially the energy space is gapped, right? So you do not have, so this, there is a band gap, right, between these two energy states. And again, this is also 2t. So in the real space, the picture is, we have energy versus position of moment, sorry, position of unit cell, let's say, and there are discrete energy states, as we know from atomic picture. And in the half filling case, you have electrons sitting at each energy lower energy level, and then in the momentum space, the picture looks like something like uh, so again we have energy versus k. We have a continuous energy of t, and these are energy of t and minus t. Again the same thing here, t and minus t, and the electrons are occupied in the lowest energy states. Okay, so what we call these two scenarios is that this is atomic insulator and this is band insulator. Okay, so why do we call this atomic insulator is because so we are seeing in the real space picture where this is one unit cell, this is another unit cell, and then in the because in the unit cell there is two atom and each atom have identical orbitals. There is two energy states, and out of that one state is fully occupied, and there is a finite gap in the energy of 2t uh, from if between these two states. Okay, so this makes it an atomic insulator in the atomic picture. And what makes it band insulator is that we are in the finite band picture, right? So there is a continuous energy spectrum as a function of k, and there are two bands. So this is, let's say, first band and this is second band, and the first band is the lowest energy band, which is fully occupied. There is no energy states available, and essentially that means that will mean that there is a band gap between the first band and second band of the amount 2t. So this is a band insulator. Okay, but they essentially represent the same thing, right? If you apply current in the system or some electric field, they will not conduct electricity. So in this sense, these atomic insulator and band insulator are sort of same. Now, what we have done here is that we assume that the hopping is independent, uh, or hopping is constant of t, right? So if you have a Hamiltonian which something looks like something like this, so earlier we had a Hamiltonian of t minus t 0. So now let's say we have a Hamiltonian of 0 f of k. Okay, sorry, if star of k, let's say, because the Hamiltonian must be Hermitian conjugate, right? Hermitian basically, because then it needs to be half, sorry, star. So f of k is some function of k. Okay, so we are talking about K space picture. So some function of crystal momentum K. Okay, so if this is the case, and if you solve this Hamiltonian, you will get uh, the energy spectrum something like this. Again, we do not have a I mean exact picture, because essentially we need to know the form of Fk, how it varies with K. But what I'm trying to convey is that in this case, in even in the K space, the Hamiltonian was simply minus t 0, and t is real, so t star and t are same. Okay, t are same. So this was the Hamiltonian in both the K space as well as the real space. Now, if we have a Hamiltonian in the K space where instead of t uh, being a constant, we have something, let's say fk, let's assume that minus t of e to the power ik. Okay, so this is a function of k which varies at different values of k, right? So that means there will be variation of k, let's say. So these are some random function of k. Okay, although e to the power ik is, I mean, it has a will uh, be a value, but I'm just trying to convey the key message, that even if you have a k dependent terms in the Hamiltonian, and if you are dealing with this kind of situation, so this kind of situation, and then the hopping is dependent on k, let's say. Okay. So what will happen is that there will again be this type of I mean bands which will, instead of being constant, there that will depend on crystal momentum, but essentially you will still have insulator. Okay, because these are, let's say, bands, and again they are uh, there is a finite band gap everywhere. Okay, and what we have assumed here is that f of k is always 0, sorry, always greater than 0, so that it may, so this type of situation we are not considering. There is a band gap closing and so on. We'll consider this as we go along. So this was one set of band insulator, okay, which kind of same as the atomic insulator. So the key message for this is that so there is some set of atomic insulator, or band insulator, let's say, which are same as atomic insulator. Okay. Uh, so this we assume, so this conclusion is valid for a system or only chain where we took that this is, let's say, B type atom, A type atom, and this is the unit cell, and then it continues A, B, and there is n number of such unit cells. So this is, let's say, ith unit cell. This will be I plus 1th unit cell. So this part, and the hopping between this A and B is that this one and this one is allowed with a finite probability of, or hopping amplitude of minus t, but then there is no such hopping. Okay, so the intracell hopping is finite, what we have studied in. So this is unit cell. Intracell hopping is given by minus t, and intercell hopping is not there, which you can say that, in other words, you can say that intercell hopping is 0. Okay, and in this scenario, we have, what we have seen is that there is two complementary picture. One is the real space picture, which is the atomic insulator, and then there is a momentum space picture once we go to the periodic system and infinite system, let's say, which is the band insulator, and they are equivalent of each other. Okay, in both the scenarios, we have a, I mean, insulating states and two energy states of having same energy, plus T and minus T. Okay. And then we'll go to the next case where the scenario will be exactly opposite. So what do we mean by opposite scenario is that we have again unit cell of A type and B type. Okay. So this is the unit cell, and this hopping is allowed. Okay. and there will be somewhere another A type, B type, and then it continues in both the direction. So this is, let's say, unit cell. Uh, so this is one unit cell, and then from B to A is allowed with a finite hopping probability of minus t, let's say, minus t, and then of course this is also allowed, right? But then what is not allowed is this. We are not considering this, okay? We'll solve these scenarios and go ahead. So before that, if you have any question, please ask. Any questions so far? Please unmute and ask. So no questions. Okay. So if you take this particular scenario where the intra-cell hopping is allowed, whereas intra-cell hopping is not allowed, then the Hamiltonian we can write, or yeah, so the Hamiltonian we can write is that, so we have a Hamiltonian again in the real space picture. I'll sum over all the unit cell. So this is, let's say, ith unit cell, and then I have hopping amplitude of minus t, C I B dagger, C I plus A, or let's say if I being consistent with the figure, then what I'll do is that Ci plus 1 dagger and A type, Ci of B plus Hermitian conjugate of it, right? And this is, let's say, I plus 1th unit cell. So this is I plus 1th unit cell. So what I am essentially doing is that I am creating an electron at C I plus 1th. So I plus 1 means I plus 1th unit cell, and then in the A type of atom, right? So this is the creation operator. So I am creating, and then I am annihilating an electron from the ith unit cell from the B type of atom. So that's what it essentially means. So this term, this particular term is corresponding to this process. Okay. So I am annihilating an electron, essentially equivalent to saying that the electrons from the B type of atom from the ith unit cell is moving to uh, A type of atom of the ith plus I plus 1 1th unit cell. Okay, and then it's Hermitian conjugate. Okay, so this is the real space picture of it. And again, what do you think is going to happen? Again, essentially, we'll have same thing. We'll have a lot of energy state if we go into the real space. So this is energy of plus t, this is energy of minus t, let's say, right? Essentially, nothing difference happened here. Just the rule of intracell and intercell hopping gets interchanged, right? Earlier we had a intercell hopping to be 0, here intracell. So intracell hopping is 0 here, okay? So we'll have an energy state of plus t and minus t. Again, there is a band gap of 2t. So again, if they are half filled, the electrons will sit here, all the low energy state of minus t, and then it's again an insulator, right? Okay, okay. Now if you go to the momentum space picture of it, so this was the real space picture, and then if we go to the k space or momentum space picture, Again, you need to do the Fourier transform. Okay. Uh, so what we will have is that we have something like this. So everything I am not deriving, of course, because of time. But yeah, I'll suggest some reading, some references where you can read about more of this actually. So Hamiltonian will be minus t, again sum over k, and we have two kind of states, right? Uh, CKA dagger. So note that here there will be no unit cell index because we are essentially whenever you go to the Fourier transform, you essentially assume the system is periodic, and then so the unit cell are sort of it doesn't matter that you label this unit cell, so this unit cell to be ith or this unit cell to be ith because periodic, right? So you can just go around. So CKA, and then so this is a actually matrix. So this is a row matrix, CKB dagger, and then there will be 2 by 2 matrix. So this is let's say 1 by 2 row matrix, and then 0 e to the power uh, minus ik e to the power minus ik star means it will essentially it will be plus ik. So e to the power plus ik 0. I will explain how you can arrive at this expression a bit briefly. And these are the I mean annihilation of it. So what we have essentially done is that we have done Fourier transform. So I had the operator Ci of A, let's say Ci of A dagger, right? And once you do Fourier transform of this operator, so what you do is the L is the length of the system, let's say, and then you sum over k e to the power minus I k. Uh, so this will be I times the, so there are two I, so I need to be careful. So I k delta, let's say, and then C k a dagger. Okay, so delta is the distance between inter-unit cell, inter-unit cell. Okay, so so if I go to this picture, so this is let's say delta. Okay, or earlier I said it to be a. So this is let's say this length is a, let's say. Okay, so this length is length or equal to delta, let's say. Okay, or let me write it a as better. So this is a. Okay, a. So what is the distance of unit cell between these two unit cell is that a, and this is also a length of a. So since we are having the hopping from one unit cell to another unit cell, so this extra length scale comes into the picture. Uh, so so this is so from this midpoint of this unit cell to the midpoint of this unit cell will be also a, right? So in the picture it doesn't look like this, but if you read about the tide bending picture, tide bending Hamilton, and then you'll actually it will become more clear. So so that's how the a comes into the picture, e to the power I k a. In earlier case, we had e to the power I k or let's say minus I k into 0 because those were only intra-unit cell. Okay, so initially we had intra-unit cell hopping within the unit cell itself. So e to the power I k into 0, and that means it was 1. And that's why you got 0 minus t. Okay, I should have, okay, minus t is already there here. So minus t 0. So in the earlier case, okay, there was no e to the power I k because e to the power I k into 0 was just 1. Okay, so this is how we do Fourier transform. In our all the cases, we will assume that A to be 1, so A equal to 1. Okay, and this is the Hamiltonian in the K space. So, so if we solve this Hamiltonian, 0 e to the power minus ik e to the power plus ik 0, and again and there will be minus t multiplied here. So again you will get two energy plus minus t, but this time energy eigenstates, if you solve h psi equal to, let's say, energy of E psi with this energy plus minus t. So if you just I mean diagonalize it, or let's say eigenvalue, you determine the eigenvalue, you will get only plus t and minus t. And if you solve this equation, then you will get two states. So we have, let's say, energy eigenstate of minus t, and corresponding wave function is going to be given by let's say psi will be 1 by root 2 uh, 1 e to the power ik, and then energy eigenvalue of plus t psi will be given by 1 by root 2 1 sorry minus 1 e to the power ik. Okay, so these are the two energy states. So this is a low energy state and this is a high energy state, right? So this was the case for so when the intracell hopping is 0 and intercell hopping is there, the wave function changes, but the energy eigenvalues remain same, and the system remains an insulator. Okay, so in both the cases, so scenario one we considered. So let's say uh, case one, we had intra-unit cell hopping, and then case two, inter-unit cell hopping. So what is the similarity? Both are insulator, both are band insulator, you can say, with band gap of 2T, right? When it is half filled. So this is the similarity. Now, what was the difference? In case one, we had simply eigenstates as 1 by root 2, 1, 1, and 1 by root 2, 1 minus 1. And in this case, 1 by root 2, 1 e to the power ik, and 1 by root 2 minus 1 e to the power ik, right? So the wave function differs. Wave function is different. So you already get a feeling that depending on the hopping strength, you have a band insulator. So if you look at the energy spectrum uh, in the atomic state, or in the real space picture, you will see there is nothing different. So there will be many states like this, plus T and minus T. So they will look, or they will behave as an insulator, but then their wave function is different, right? So that's the first difference that we notice between these two scenarios, and then we'll see more difference in it actually. Okay, now before going to the next stage, we're only talking about the half filling, let's say, right? So the electrons are filled in the low energy state. So what if the states are not half filled, meaning more than half filled or less than half filled? So let's say, so we know that at the half filling, the system is insulator. Why? Because there is a finite band gap of 2T, right? So half filling, we have band gap of 2T, right? And system is insulator. Now what if we have a less, so let's f equal to half filling, right? It will be easier to write. So let's say what happens if f is less than half or f is greater than half, then what will be the scenario? So even if you see in the atomic picture, I mean real space picture rather, so we have an energy stored.
Hello,
Yeah,
Sunit.
yeah.
So are we assuming that both A and B are having single electrons each, which can hop from one to other?
We are considering, yeah, single orbital, single electron. Yeah.
Okay. And also this concept of unit cell, like that
Hmm.
is something that we assign, right? The material actually doesn't make a difference between, let's say, you have A, B atoms arranged periodically. So whether we consider,
No, it depends. So for our case, for simplicity, we have not considered that there are other orbitals, and then we have also considered that A and B type of atoms having same orbitals, right? These
uh,
are our theoretical construction. It can
okay.
happen that in some materials it might be the scenario actually, but for most
Okay. So
materials
now
it
what I'm asking is, like, let's
Mhm,
say we say that the first A and B constitute the unit cell, then we say that the next A and B is the next unit cell. So, like, that is our construct, right? Like, it could well be that B and A makes a unit cell, then the next B and A makes a unit cell.
yeah, that doesn't make any
So,
difference, right?
uh, so
Yeah.
what we when we say that there is no hopping between unit cells or there is only intra unit cell hopping.
Hmm, hmm.
So, does the material actually make a difference between those two scenarios?
Okay, so right now we think that, or we feel that there is no difference. Actually, these are theoretical construct. Okay, in
Okay,
real scenario, based on this, there will not be any difference. Okay,
okay,
but
okay,
what so in the next step itself, what we are going to consider is that, so these are extreme cases. So as a condensed matter
okay.
theorist, we really need to solve very small problems to understand the physics of it actually. So, and we always
Yeah,
try to construct the very smallest possible toy models, even it is
okay.
practically
Yeah,
possible.
fine. That I mean that is fine. The toy model is fine. But what I was asking is whether this intercell and intracell unit cell
Hmm.
means you said there is a noticeable difference in the wave function if you have
Yeah, yeah,
intracell
yeah.
unit cell.
Hmm, hmm.
So that is what I was asking. Like from the material point of view, it is just saying that the electrons can hop between two adjacent sites.
Right, right.
Whether we say it is inter unit cell or intra unit cell, does it make any difference to the material actually? Like
No, for this scenario, it will not make any difference. Okay,
okay,
it
okay,
will be
okay,
only be visible. Only there will be visible difference when we consider both the limit. Meaning,
okay.
here we took extreme limit that either intra-unit cell hopping is zero or inter-unit
Mm.
cell is hopping. There is nothing in between, right?
Okay,
In this
okay,
scenario,
yeah.
it will be
Mm.
different when both the hoppings are there, but they can be of
Mm.
different magnitude, and that's the more
Okay,
realistic scenario.
okay, okay.
So then it will be actually make visible difference in both
Okay.
energy
And
side as well as
here from a physical point of view, when we are saying that the electrons can hop only between the adjacent things,
Mhm.
then it is kind of natural to assume that it is going to be an insulator, right? Because there's no what do you call the material scale transport of electrons possible because they are not only allowed to hop between the adjacent two sides.
uh,
Is that uh,
uh,
right?
no, actually. So
Okay.
let's see. That was what I was trying to come, but yeah.
Okay. Okay.
So
Okay. Okay.
so
Okay.
only in the
Yeah.
case of half filling. Okay. So only if we have half filling, then all the lowest state is sort of I mean filled up. So every time electron has to sort of transport, then they need to overcome a energy barrier of 2T, right? So that's what we call it insulator. There is a finite band gap at each stage. Now, what is the scenario in this case itself? Okay, in these two cases itself, less if we have half fill, less than half fill. So what we'll have is that I have some states, atomic states like this, and the electrons will be there somewhere here, and yeah, so less than half fill, let's say. So less than half fill. Now, what can happen? is that whenever there is a inter-unit cell hopping allowed in the second scenario, then because there is a finite, I mean, so there is a state there, the electron can hop here, right? So then there can be, so then the system will not be perfectly insulated because the electron has a finite probability of turning into the next unit cell. So they can conduct electricity. So that will be kind of metallic state, less than half filling, or the similar scenario will play out if we have, let's say, electrons here, here, and then somewhere here. So the whenever there is inter-unit cell hopping allowed, then we'll have this metallic state. I hope
So
this.
what actually decides whether it is less than half filled or greater than half filled?
Uh, it is actually decided by the number of electrons that you have. Actually, this is decided by the two scenario. So any realistic material you consider, uh, essentially we are in the periodic limit, right? You have a fairly big 10 to the power 23 at least. That is the order of number of unit cell, number of atoms, and so on. Even in the smallest nanometer size materials, let's. Uh, Actually, it can be less also for 2D materials and so on. But what is important is that depending on the system size and so on, you will have a finite number of states, right? And that finite number of state is also very fairly large. Uh, but what it determines is that how many number of states are there and how many number of states are filled. So what it necessarily means is that if the all the energy states are filled, then depending on the energy spectra and so on, it can be either, I mean, it can be metallic. So if we give more concrete example, let's say I have a band structure something like this, okay? Or even the simplest case, I can consider we have a square lattice. So square lattice band structure will be something like this, right? And let's say there are number of states. So this is the lowest energy state and this is the highest energy. So square lattice will be something like this. You can, so there is a single atom and then it continues. Okay, single atom, single orbital, single electron, simplest possible case. So this is the lowest energy state and this is the highest energy state. So these are the available energy states. So this is energy and this is, let's say, k. So at each point there is available energy state, okay? And for, yeah, so for now what will happen is that, let's say, this is the filled up state, or this is the, up to this the electrons are filled, okay? So all the states corresponding to this energy, corresponding to this highlighted energy, are filled. Now even if it is half filled, let's say, so this is, let's say, half filled, and there are equal number of states here which is not filled, okay? The number of electrons in the system is such that, now if we apply electric field, then there are available states, electron can go to the higher energy and then they can conduct electricity. So this is essentially metallic, okay? Is it clear for this part?
Yeah, yeah, yes.
Even if it is half filled, it
So,
depends on
so
the
in our
system.
case,
Hmm.
it might be like, let's say, in one unit cell, the electron might be in the upper energy state. So, an electron from the nearby unit cell can hop to this particular unit cell, this
So
vacant lower energy state that is available.
so
Is that kind of how it works?
it always works from the, so electrons always fills up the lowest energy states and then it,
Hello.
so I have a internet problem. Sorry, what happened? Oh shit. It's the problem. So disconnected from here or not? Hello, am I audible?
Yes, yes, you're right.
Okay, I just got disconnected. Let me share the
Okay.
screen. It is already. Okay, so what was the question? Yeah, so we are discussing this half filling case, right? So energy,
Yeah, yes.
sorry, the electrons will always fill from the lowest energy state to highest energy state. Okay, there are exceptions to it, but then let's consider only the simplest scenario. So uh, we have a square lattice, and then the electrons, let's say half. So the total number of available states, let's say n, and then the electrons we are having in the system is that n by 2. So the filling factor F is n by 2, how many of them are occupied by how many of them are available, maximum number of states. So this is simply half. Even if this is half fill, the system is metallic for a this square lattice case. On this square lattice, I should not call it on this square, but even for 2D it will be the same actually. So this will be kx, and similar distribution will be also available qy. This is difficult to visualize in 2D, but yeah. Now, imagine you have a system where band structure looks like this. Okay, this is the scenario for graphene, let's say. For graphene, it happens that the band structure looks like. So I'm not going to draw the full picture of band structure for graphene, because full picture is something like this. But we are essentially around the, let's say, Dirac point. Okay, so this is, let's say, around K point, Dirac point. We'll see in the quantum hall lectures. We'll explicitly see how this band structure arises. And this is the energy, and this is the momentum. Okay, and let's say, and in it naturally happens for graphene that we have a. I'm just stating the facts. We'll see the details in later lectures. So graphene have a this kind of uh, unit cell, A type of atom, and then B type of atom. Again, both are pz orbitals, carbon atoms, and if you see the number of atoms, so carbon essentially having 6 electrons, right? So 6 electrons, 6 protons, and they're distributed in such a way that one of the pz orbitals is fulfilled, or sorry, yeah. So what will happen is that there is a hybridization of pz, sorry, px orbital is p2 and then pz. So the pz orbitals are filled. The number of electrons in a neutral graphene or carbon uh, is such that these states are filled. Okay, so these are filled. The number in a neutral graphene, you have not done any external influence on it. So the number of electrons is such that this is fully filled. Okay, this is fully filled means your chemical potential is somewhere here. So that's how we define chemical potential, right? The Fermi energy is defined that up to which energy at zero temperature the states are fully filled. So that's how we define Fermi energy. So your Fermi energy is here, and these states are filled, and the equal number of states are there in the upper band, but they are not filled. They are they are empty. So if we have this scenario, then the system is semi-metal actually, meaning at this exact point, at this Dirac point, you have a density of states will exactly vanish, and then density of states increases as you increase the energy. Okay, so depending on the system, band structure, and so on, at half filling, the system can be metallic, semi-metallic, or insulating. I hope this is clear. Or any questions, please ask.
Okay, then. Okay, got it. Okay.
So for our scenario, half filling is, insulating, because there is a band gap already at the half filling. But even if you, whenever you have less than half filling, this scenario, then whenever there is inter-unit cell is allowed, hopping is allowed, you will have metallic system. And again, the same thing, more than half filling, inter-unit cell hopping is allowed, again metallic. Okay. So yeah, so there is no universality in the sense of half filling or less than half filling.
So
Yes.
here, what is less than half filling and more than half filling? What is the difference?
The difference is, okay,
You always talk in terms of the lower energy level, or?
So yeah, yeah, in terms of lower
Okay.
energy. So whenever F is
Okay. Okay.
greater than half, so that
Mm-hmm.
means
Okay.
the field states, number of occupied state, occupied state is, let's say, and the total number of state is always 2n, right? For our case. So the number of occupied state is less than 2n, actually less than n, that then only it will be less than, less than half, yeah. So this half is, let's say, make it constant here. So if the number of occupied state is less than n, then this is the, okay, I need to make this less than half
Means
filling.
in terms of the lowest energy level.
Yeah, less than half filling means, yeah. So your these states are, I mean, not occupied, right?
Okay. So the electron in our model, that electron will be in the upper energy level.
No, not, you don't need to go to the upper energy level. It can just hop. There is a on state here highlighted in yellow color. So the
Mm.
electrons can hop here and then conduct electricity. That means it's a metallic state, right? So if you look at the in terms of band structure in the K space, again this is just a rough way. The K space band structure will let's say something look like this. Okay, your field Fermi energy somewhere looks like this. So that there are states. So this is, let's say, a high energy state T. Okay, and it's a function of K. Let's say some function of K. So this is energy and this is K. So what is happening here in the less than half filling is that you have a Fermi energy here, so that the electrons up to this point are filled, but then there are some state which can go here. Okay,
Okay.
get my
Okay.
point? Even this
Yeah.
is
Yeah.
the
Got.
minus T f of K, within the same band electrons can hop.
Okay. Okay.
And for the greater than half filling, the scenario is exactly opposite. So Fermi energy somewhere here, so that the electrons are filled up to here, but then it can go to here. Okay, so these are the two extreme scenarios. Either intercell hopping is allowed or intracell hopping is allowed. Now, before considering the case where both will be there, uh, it's not a digression, but it is important to understand the next step. Uh, I'm not sure how much I'm going to cover it, but I hope this is important and useful. So what we are going to consider is that consider a general Hamiltonian in general 2 by 2 Hamiltonian, let's say. So we are having two unit cell, two atom in the unit cell, and both of the atoms are having single orbital. So that's why the Hamiltonian for both of the cases was 2 by 2, right? And we are solving again and again. So let's consider the general 2 by 2 Hamiltonian, keeping the same system in our mind. Okay, but yeah. So let's assume that Hamiltonian is something like this, and this B represent the real magnetic field. We'll explain why we are considering this and what this means. And then this sigma is essentially sigma x, sigma y, and sigma z. Okay. Okay. So this what this necessarily mean is that the magnetic field has component along all direction z, and if we represent in this pictorially, so this is the B direction, and somewhere here, let's say, so this will be phi, spherical polar coordinate. So phi and theta, right? So B will be represented, B will have component B, let's say, sine theta cos phi plus I cap or X cap, let's say, plus B cos theta, no, sine theta cos phi, plus B cos theta.
People with sine theta.
Okay, so if you write the Hamiltonian in the matrix format, so what will happen? So this is our Hamiltonian, and n cap is just the I mean unit vector. So n cap is essentially x cap plus I cap plus z cap, right? And of course, it's an unit vector. So let me write in the vector form. So y cap z cap comma. So if you write in the matrix form, Hamiltonian is going to be minus b, and we use this form of magnetic field. So full screen it. Yeah. So b minus b, and then cos theta. Okay. Yeah. So it will be sine phi, right? And then what will happen? So this you can work out. Okay, I am not writing. So you can write that as sine theta e to the power minus I phi, and then sine theta e to the power I phi and minus cos theta, right? So these are the just if you expand in terms of sigma x, sigma y, and sigma z, you will get this Hamiltonian. Now, what will be the energy? Energy eigenvalue just simply plus b and minus b. You can just work out this. I mean, uh, determine its eigenvalue, and the wave function. So once you have the energy, you will solve the eigenenergy problem. So let's say these are wave function, and then you will take plus b and minus b. So for minus b, when energy is minus b, our eigenenergy state or psi will be something like this. This is a standard result, cos theta by 2 sin theta by 2 e to the power I phi. Okay, and then when energy is plus b, psi will be, let's denote it psi minus, psi plus. It will be sin theta by 2 minus cos theta by 2 e to the power I phi. Okay, now so this is a function. So this is a energy eigenfunction uh, as a function of theta and phi, right? Now in spherical coordinate, or which we also call the Bloch sphere, how can we represent this two eigenenergy state? Okay, things will be clear why we are doing this. Okay, so hold on. So suppose we have so yeah, let me draw it again. So this is, let's say, x, y, z, and we have some vector. Uh, so the states can be represented by this. We have phi and then theta. In the so this is a whole sphere. Okay. If we draw full, so this vector which is b will be sort of full circle. This should be fully symmetric, but leave it. Okay. Okay. So depending on where the b is, our state is going to be which state the b value is going to be positive. So let's say we have b positive, some b positive, right? So positive is happening. Yeah. So let's say we have this is plus b. So this full half quadrant. So this is, let's say, the plus z quadrant is determining my plus b. The magnitude is already given by always plus b, and then the state is determined by this, right? And depending on the position of b, the state can be here, here, right? And so on. So what this hk gives you, or in the Bloch sphere gives you, that uh, you can represent the states psi plus and psi minus in a Bloch sphere, given that you have k. So okay, so let me explain it again. So this scenario we have considered is that Hamiltonian of minus b n cap dot sigma. So this is like a spin half problem, right? You have a spin up and spin down, the two state possible, and then they can represent other state depending on the superposition of spins, right? And in the full block sphere, you have a huge number of states depending on the spin is here, 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 or here, exactly opposite. So you can think of this problem as spin half in presence of a magnetic field, right? So is spin half in uh, presence of B. Okay, and given that our Hamiltonian is also in our case, the in the case two at least, we have seen that we have a Hamiltonian of minus, so minus t e to the power minus ik e to the power plus ik 0. So once you know, so this Hamiltonian can be mapped to the Hamiltonian we are studying now, right? So right now we have a Hamiltonian of Vn dot sigma. So we can determine the where the state lies in the block sphere, similar to this problem. Okay, and we'll see the importance of knowing this. So so in the first scenario, so let's consider case one. So where our Hamiltonian was uh, 0 minus t 0, right? So only intra-unit cell hopping was non-zero. Okay, was let me write it. Hopping was minus t. So this was our Hamiltonian for case one. So if you map this Hamiltonian to this scenario, or let's say this, make it equation one and then equation two. So compare one and two. Okay. So what you map here is that we have bx equal to minus t, by equal to 0, bz equal to 0, right? So, so where our Hamiltonian was? Yeah, this one was our Hamiltonian, minus b, and then these parts, right? So we have minus t. So let me write it explicitly, then you will understand. So we had a Hamiltonian of minus b cos theta sine theta e to the power minus I phi, I think, or plus I phi, minus uh, sine theta e to the power plus I phi minus cos theta. Now compare these two. So minus b is already minus t, right? And we have here 0. So we have 0 in the diagonal terms, where what that means is that cos theta equal to 0, cos theta equal cos of minus cos theta is also 0. So what that means is that theta equal to pi by 2, right? We are only in the, let's say, I mean, of course, the multiple of pi by 2, but considering, let's say, pi by 2. And then this sine theta is essentially then 1 pi by 2. Then e to the power minus I phi is also 1. E to the power plus I phi is also 1, because minus b is already minus t, right? So in the block sphere, what this means, whenever you have theta by pi by 2, that means that you have a z, y, x, your magnetic field is already in the plane, right? So this is theta by theta equal to pi by 2. Now we need to determine what is phi. So phi, when e to the power minus I phi and plus I phi is also, I mean, both are 1. So we have cos phi plus I sin phi, right? So 1. And then cos phi plus, sorry, minus I phi minus I sin phi equal to 1. So you can determine that phi is 0. This is one of the solution. Of course, you can have phi equal to pi as well, but so phi equal to 0. That means your magnetic field is aligned along this direction, x direction. V is parallel to x. So that's why we are calling it that in this scenario, Bx is essentially minus t, By is 0, Bz is 0. Okay. So what this necessarily means is that the states for this equation 2, for case 1, you can represent these states in the Bloch sphere along the direction of x. Okay, so let me rephrase it. We had a Bloch sphere, right? Uh, and then we already know that we are in the theta equal to pi by 2 limit. So essentially your states for this Hamiltonian equation 2 all lies in the xy plane. So essentially they will all lie in a circular region, right? It will not be in the 3D space because you have already projected it. Your the states are such that Hamiltonian is such that you do not have any z component, right? So the Bz is 0. So so if you draw a circle and this will live in the x. So let's say this lives in the xy plane. Okay, so this is y, this is x, and in which direction the wave function will be I mean aligned. Let's say I'm talking about the lowest low energy eigenstates, right? That's where we are interested in half fill case. So we just saw that the component will be bx equal to minus t. So bx along the bx direction, right? So, and this is the scenario. So all states at each k is lying along. So yeah. So this is the Bloch sphere in the K space, let's say. Remember we are in the case 1, and it doesn't depend at which K you are in, even though we are saying that Bloch sphere in the K space because your Hamiltonian is essentially independent of K, right? So at each K it doesn't matter where you are, at which K you are. So let me write and then explain. So the ground state essentially means energy equal to minus T. Low energy states, the Bloch vector, we are calling this vector as Bloch vector for the wave function, or the Bloch vector is fine, is oriented along x cap at all k values. Okay, so this was a Bloch sphere in the, so this was a Bloch sphere in the K space. So at all k values, crystal momentum values, your ground state wave function is along the x-axis. Okay, so please, if you have any question, please ask. This is very important uh, concept. So do you understand why we are mapping the wave function? Essentially, we have some wave function, and we are mapping the wave function into the Bloch sphere, or in the in the K space, let's say. So everything is clear now?
Yeah, it is clear. And the upper energy level will be in the opposite direction?
Yeah, opposite direction just, but they will be essentially parallel, right? Parallel to x.
Okay, okay.
Okay. So let me go to the next case 2. Okay. Now let's say we are in the case 2. Case 2 Hamiltonian, in our case was minus t 0 e to the power minus ik uh, e to the power plus ik 0. Again, we have bz to be 0. There is no diagonal elements. So, and then there will be both bx will be something non-zero and by will be something non-zero. So, we can actually determine it. So, so what we have is that bx comma by equal to b, it will be sine phi b cos phi, right? Or the vice versa actually. And here we have b equal to minus t. If you compare this, uh, yeah, or minus b equal to minus t, and e to the power ik. This was the case. Not was the Hamiltonian. This was the e to the power minus I phi. So, so what will happen is that so to the power minus I k is equivalent to the power minus I phi, right? And the wave function for the lowest energy states is going to be what we have already defined, this one. Now what we have additionally right now is that your theta was already so you had theta equal to pi by 2, right? So that means that cos pi by 4 and sin pi by 4. So this will vanish. I mean, it will be just 1. It will just be 1 times e to the power I phi, and then there will be root 2, right? Both are cos pi by 4 and sin pi by 4 is 1 by root 2. So this is the value of cos of pi by 4 equal to sine of pi by 4, because we have theta equal to pi by 2 in our case, and this comes from bz equal to 0. Uh, am I right? Yes, cos theta is 0. Yeah. Now this gives me e to the power ik is equivalent to e to the power minus I phi. So depending on the k, my so we have both the scenarios. I mean, bx and by, both components are there. So earlier we had a case where only x components was there, but in this scenario, if you draw it, this will look like. So if you draw carefully, what will happen is that your direction is going to be something like this. So you started from this. Now, how do you see that, right? That's the question. So this was x. This is, let's say, y direction, and we are in the already in the plane, right? Bz equal to 0. So xy plane again, and this was, let's say, theta. So this was the direction of any vector, and this was sorry, this is not theta. This is phi. Now Now take the scenario where phi is 0. So what happens? So psi is then going to be 1 by root 2, 1, and e to the power minus I phi. So sorry, e to the power plus I phi is there. So when phi is 0, then e to the power 0 means 1, right? When phi is, let's say, pi by 2. So this is for the phi equal to 0, phi equal to pi by 2. Uh, so psi equal to 1 by root 2, 1, and then what will happen? E to the power I phi by 2. So iota, right? So this is another scenario. So remember that in this case, so in this in the case one, we always had represented along the x direction because our psi for the low energy state was 1 and 1, right? So 1 by root 2, 1, 1. So this was the our psi state and it was always along the direction. So let me go back to the very first thing we did. We'll connect things then. Uh, so our where was a psi? No. Yeah, so this was the psi actually. Bonding orbital. So this was the psi. Bonding orbital, I mean, energy is minus T, so low energy state, right? For the first case one. So this was for the case one, it was always oriented along the x direction. That's what we have done. Now we are sort of making it to be reference, right? So this we are representing by x cap along the x direction, which is phi equal to 0 case. And then when phi equal to pi by 2, we can, so this is, that's 1 and iota. So this we are representing along the y direction, having finite component along the y direction, right? dy. And then whenever phi equal to, let's say pi, then what will happen is psi equal to simply 1 by root 2, 1 minus 1, right? So this is phi equal to pi, and this is phi equal to 0, and this is pi by 2. Okay, so the crux of the story is that even both the cases for the so this is case 2. So in the both the cases, in the half filled case, the energies were same. I mean, the energy landscape was same. In both the cases, you had I mean, this kind of states, and then half fill case. So these are the fill levels. You had a band gap of 2T, and the system is insulator. So this was for case 1 plus case 2. What is different in these two scenarios is that their wave function in the case space looks completely different. In one scenario, this was my energy, block states looks like all oriented along the x direction. Let's say this is our reference state, and then for the case two, so so basically they changes in the as my k also changes, right? So the block vectors, we can say in this case two scenario, that block vector twists in the case space. Okay, and this is what is called band twisting. Band twisting. What this necessarily means is that so the wave vector direction in the block space or block sphere space, it changes its direction as we changes the k. Okay. Okay. Now, how do we measure this twist? Right? We now understand that even though energy-wise both the insulators are different, case one, same. Case one and case two are essentially similar. I mean, insulator in terms of block vector, in terms of energy. Uh, but then there is some difference in the wave function, right? It's a 2 by 2 system, so it was easier to visualize things. But then once you go to the higher dimensional case, I mean, the Hamiltonian will have, let's say, 3 by 3 Hamiltonian, 4 by 4 Hamiltonian. It will be very difficult. So there should be a way to see that does that wave function is kind of trivial. It is along the, let's say, this scenario along the x or along the only y, along the only z, or this kind of scenario happens where in the block space it changes its direction, right, as we changes the value of k. This is faithfully kind of tracked by something called winding number. So this is defined for 1D scenarios, 1D systems. For 2D systems, for 3D systems, there is something called vary phase, or better to call it churn number. Vary phase is something related to churn number in 2D and 3D. Actually, it is strictly defined for 3D, but sorry, 2D. But then for 2D, we also call it churn number by cutting, I mean, by looking at some at a particular kz value, let's say. Okay, so we'll see chart number we will extensively see in quantum Hall effect as well as quantum anomalous Hall insulator, quantum spin Hall case also we can see, and then if the time permits, we can also look at topological semimetals. There we'll see chart number at a finite kz. Okay, okay, so this winding number is given by I pi minus pi to pi. Minus pi to pi means, let's say you start from here, so this you call it minus pi, and you I mean you, so you start from minus pi and then you go to till the whole point, and then you go to the plus pi. Okay, so this is plus pi and this is minus pi. Okay, let me rearrange this thing. So minus pi and then, so this will be plus pi. Okay, so minus pi to pi meaning full periodicity, and then let's say this was my state as a function of k, and del k, and this is 1D, so I don't need to put any vector psi of k. Okay, and this is k dk. So this, if this particular number called winding number is non-zero, so if it turns out that if w is non-zero, that means there is a band twisting. And this indicates that there is a non-trivial topology in the system. And if w equal to 0, then there is no band twisting, trivial system. Now let's see how we can prove this for our scenarios, right? So for case one, we had wave function psi of k was something like this, 1 by root 2, 1 and 1, right? So it is essentially independent of k, right? So if it is independent of k, then when we determine the del k of psi k, right? So that was the our definition, right? This we determine first. This is itself 0 always. So for case 1, this part is itself 0. What this necessarily means is that winding number is 0. Now for case 2, we had psi of k is something like 1 by root 2 1 e to the power ik or minus ik, ik. Let me see. Oh, yeah, e to the power ik. Okay. Okay. So that means that del k of psi of k is not going to be 0. There will be some finite. You can derive it. I am not deriving it already. I mean, we're almost all the time. So if you derive this psi of k, again we are in the ground state, okay? The whole analysis is we are doing for the ground state, half field. Uh, Psi k of grad k or del k psi k, you just derive it. What will you get is that it will be I by 2, I think, yeah. So then W will be, W has a formula of I by pi minus pi to pi, and this part psi k grad of k psi k, which is equal to I by pi minus pi to plus pi. Okay, this was dk, and then we will have I by 2 dk, right? So this is a trivial integration. So I square minus, sorry, yeah, I square by 2 pi, and then if you do this part, minus pi to pi dk equal to 2 pi cancels out, I square is minus 1. So what we get is that W equal to minus 1. You see that we need to explicitly map it to the I mean magnetic field in the 3D space case, and then we draw these vectors, how it changes. We determine that at phi equal to 0 it is kind of along x direction. At phi by 2 we have this component, so this is along the y direction, and then it is at phi by pi we had this, that means along the pi direction, right, minus x direction basically. So this is equivalent to minus x direction. All of this we did and then concluded that this particular picture is given where the wave function direction changes in the block manifold, right? We don't need to do all of this to see that once you calculate this winding number, this already tells you that there is some non-trivialness in the wave function. That wave function is not oriented uh, uh, only along the x direction in the earlier case, right? Rather, it is oriented in different direction in different key point. So winding number actually tells you that there is some non-trivialness in the system. Okay. So this winding number is measuring, I'll explicitly write and then take questions if you have any. Winding number is measuring how the, sorry, how the wave function, or rather the vector actually representing vector for the wave function, vector twist in the block sphere, or sometimes people also call it block manifold. So both insulators, where I am referring to case 1 and case 2, energy wise both were insulators, are different, and and depend on the wave function winds in the Brillouin zone. So this block manifold is essentially Brillouin, right? When we are saying that it's a periodic system, then we are having invoking the concept of periodicity in the system, and then in the K space there is a Brillouin zone. So in the real space we have a unit cell. By I mean you can repeat the unit cell to get the whole periodic solid state system, and then in the momentum space you can think its equivalent is Brillouin zone, on the Brillouin zone. And so so what this necessarily means is that, so this winding number, so the winding number measures this twist, and winding number is a global quantity. Why I am saying this? Because I am integrating all over the K space, right? So if you see the expression of K, so it it takes into account the how the wave function twist in the whole K space, in the of course within the first billion zone, but then first billion zone is equivalent to all the other billion zones as far as our periodicity uh, systems are concerned. So so it's a global quantity. It's an integrated over all over the K space in the Brilliant zone. So it's a global quantity that determines that two kind of systems are different or not. Okay. And then case two. So what this necessarily means is that case two is insulator, of course, both are insulator, but it is called topological insulator. Okay. And case one is trivial insulator. Okay. Both are insulators, but one is topological having winding number not equal to 0, and then one is trivial having winding number equal to 0. There is a band twisting in the case 2, and then there is no band twisting in the case 1. Okay, so what this necessarily means is that depending on the intracell or intra-unit cell or inter-unit cell hopping allowed in this kind of on the chain, you can have either topological insulator or trivial insulator. Okay, and there are other features for the topological insulator, but I think so today we need to stop. But before that, please ask if you have any questions.
So Sunit, so is there any physical difference between this topological insulator and the trivial insulator?
Oh, there is, there is. So today I'll not be able to cover, but then the physical difference is that trivial insulator, if you measure the electrical response of trivial insulator, then it's kind of, uh, I mean, it's insulating, so there will not be conduction. But then for the topological insulator, there can be conduction, or uh, if it is magnetic, of course. But theoretically, if you see that there for the topological insulator there will be zero energy modes, meaning there will be some states which are lies at the zero energy. Okay, so whenever we see insulator, we in our mind this is the kind of picture that we have, right? And somewhere there Fermi energy is lies, so that this part is completely filled, this is completely filled, so there is no states here to conduct electricity, and then there is a finite band gap, so no conduction, right? For the case of topological insulators, it turns out that there is a some states which lies exactly at the zero energy. Yeah, so this is the scenario. So this is the bulk state. Uh, uh, so let me highlight. So this is the conduction band. So this is the conduction band, let's say, and this is the valence band, and somewhere here this is the Fermi level. But then at the Fermi level, if you consider this to be a zero energy, energy zero, then there is a states which are having uh, energy zero. Okay, so this is the, I mean, one of the kind of still theoretical, and then its effect can be reflected on the transport measurements. Once your system also breaks time reversal symmetry, you will get that even in the insulating states, uh, you can have conduction. Okay, and this is this conduction of electrons, or let's say electricity, are not by the bulk state, because bulk states are already, if you see here also, the bulk states are already gapped by this much energy, so there are these band gaps, so no conduction. But there is a this kind of states, right? and these states actually conducts electricity, and these states are lives on the edge of the surface, sorry, edge of the sample. And by edge I mean physical edge of the sample. Okay, essentially uh, any system you consider, we can take periodicity and so on and so forth, but then in reality they have a physical edge, right? I mean, no system is infinite in a true sense. So if we have only system, let's say, and there can be edge state at the which exactly lives at the edge of the sample, physical boundary of the sample. It turns out, and we will also see later, that in this kind of scenario, these bulk states do not conduct, so they do not conduct electricity, but these edge state live on the physical edge of the sample. They do conduct electricity, and that's how the topological insulator can have Hall response and so on. This scenario, that in the bulk you have something happening in the with the wave function, so that you have a some topological invariant called winding number to be finite, and that kind of represents or reflects the fact that if you take a finite geometry and then calculate the edge state or calculate the states as a function of position, let's say, uh, then you will see that there are two states, or the other many other states living at the edge or the boundary of the sample. And this is called bulk edge correspondence, which I plan to cover but couldn't cover. Time is not there. So this is called bulk edge or bulk boundary correspondence, and then there is also called symmetry protected topology. So these two things are not covered. So you will see in terms of transport measurement actually.
Okay.
Okay, so any other questions? So I think so the next okay, so yeah. So the next question that I plan to address, but don't have time, is that okay, we took two extreme cases. One is intra-unit cell is allowed, uh, in intra-unit cell hopping is allowed, another one is inter-unit cell hopping is allowed. So the next question is that uh, can we go from case 1 to case 2 smoothly? Okay, so this is the crucial question where all of these concept will come. Okay, and there it will be more clear why I mean it is not possible to go from case 1 to case 2 smoothly. There needs to be something called gap closing phenomena, and then there will be the concept of symmetry protected topological phase and so on. Okay. Okay, so yeah, so this is the question we'll answer in the next lecture actually, and then there the other concept will emerge, edge state and bulk boundary correspondence.
So Sunit, the next lecture will be next Saturday, or is it somewhere in
No, no,
between?
next Saturday. Yeah.
Okay. So how does this? I mean, I'm joining for the first time for this lecture. So
Hmm.
these lectures will be on all Saturdays, right?
Yeah, the lectures on Saturday, 6 to 8. Yeah.
Okay. Okay. Fine.
And yeah, so I'm actually supposed to sort of solve some problems, but
Okay.
these are advanced courses where
Okay.
problems are not really there much, right?
Okay. Okay.
If you see the assignments, it is exactly directly sort of taken from the lectures that sir is giving. Uh, so if you have any difficulty in solving problems, assignment problems, then please ask those questions in the tutorials also, because that's the primary goal of this tutorial. And of course, clearing the doubts that we may have. Yeah.
Actually, I'm running a bit late. Like I have to catch up with a lot of lectures,
That's
so I
fine.
haven't really. And regarding the first week, Sunit, like I think the fourth lecture was about tenfold classification,
Oh,
right?
that's I think that's a mistake from NPTEL side.
Ah,
Okay,
okay.
that cannot be
Because
there.
like I started that lecture and it was already talking about SSH model, K-type chain, and all.
Yeah, yeah. That should not be
So
there. I think it's a part of second week lecture actually, this week's lecture.
okay, 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 okay. Okay.
We'll talk about a bit if time permits, but again, the problem is these are sort of advanced lectures. So, yeah. So in the symmetry protected phase, we'll have an introduction that how the different symmetry classes are introduced and how they sort of determine the protection of these states, topological protection of this, or rather symmetry-wise protection of these topological states. So topological states means there is non-trivial wave function, there is non-trivial, I mean finite winding number or some other Chern number, and let's say. Okay. Okay, so if we do not have any question, let's stop here.
So we will
Yeah,
talk.
please.
Can we talk about it in the next lecture, or
Sorry.
you said we will talk about in the next lecture, or
Yeah. This
okay,
question will I plan to finish actually, but that depends that
okay,
so again, so my primary responsibility is to help in solving the assignments and not
okay.
exactly solve the assignment problems, but uh, I mean the other problem solution and so on, so that the assignments becomes solvable, and then any queries that one may have from the lectures or from the contents that is there. But I do not find anybody questions, and people are saying that. I mean, your
But
question.
this is really useful. So it's like this is a wonderful lecture. I really liked it, and so
Uh,
this is also helpful. That's what I
Yeah,
wanted.
so what I've realized is that people, I think, find the assignment solution is pretty useful. I mean, easy to solve because the questions are actually directly asked from the lecture. So if you see this assignment also key type chain solution, and then this was directly related to, I think, lecture 7 maybe or 6. I do not know. So then also they are not people are also not much interested in solving assignments. So I thought there are a lot of aspects that even SAR is not able to cover because it's a 8 week course, so it's pretty difficult, right? So then I am trying to have a complementary view of those lectures and point of view. I mean the details. Okay.
That will be very helpful, Sunit. That will be really helpful.
Yeah, so I'm trying to
So
consolidate
it's
those things. And if you have any questions regarding assignments or regarding these lectures, you reach me out every class. I say this, but yeah, uh,
okay.
at
Okay.
sunidd uh, at the rate itk.ac.in. Okay, and try to email me at least 2 days before so that I have a look at it. Okay,
Sure, sure.
itk.
So IITK, you are Kanpur. You're from IIT
Yeah,
Kanpur.
yeah, yes.
Oh,
Okay, so let's stop for today. We'll meet on
okay,
next Saturday.
okay.
Okay,
Thank you.
thank you
Thank
for
you so
joining.
much.
Yeah.
Yeah.